So without further ado, I will introduce Willy Aspinall, who's going to give us our first talk. Willy is retired now. He's the Cabot Professor of Natural Hazards and Risk Science at the University of Bristol. And please, Willy, talk to us about expert elicitation of scientific uncertainties using Cooke's classical model, applicability to COVID-19 risk assessments. Thank you. Over to you.
Okay, thank you very much, Phil, and good afternoon, everybody. Quick manifesto statement. Steve, Sparks and I are both volcanologists mainly, although I've got a much wider brief, and we attempted to get our experience of managing volcanic eruptions and what we'd learned about scientific advice and conveying it and protecting public to the Royal Society ramp thing. And basically back from SAGE came, what do volcanologists know about viruses and pandemics on that? So this is a bit of a manifesto for our approach. And what I'll do is briefly go through a little bit of background before leading into what we've been starting to do for the COVID-19 risk assessments. So the first slide, this takes us back to 1976 and a debacle in the French island of Guadeloupe in the Caribbean when a volcano got very restless and 75,000 people were evacuated, and then the volcano went to sleep. What transpired there was that the scientists aired their differing views in public, in this case on television in Paris, and it all became rather Gallic and not very productive. And I was there at the time taking part in monitoring, and I thought, well, this is no way to conduct, scientific assessments for volcanic crises. So in 1993, colleague Gordon Wu told me about Roger Cooke's expert judgment methodology using the classical model. So we wrote a paper for a meeting in Rome saying how, well, this could be useful for eruptions. It was roundly condemned by a couple of senior leading Italian volcanologists. And I can only mention in passing that one of them was later charged in connection with the L'Aquila earthquake disaster and the disastrous scientific advice there. So, I thought, well, I'll write this paper and we'll put it in the literature, little expecting that within a couple of years, a British volcano in the island of Montserrat would itself become restless and I would become deeply involved. Well, it gave me the opportunity there as the governor's advisor to introduce expert elicitation. We used Roger Cooke's classical model and the theory of scoring rules to guide how we synthesized expert judgments about the future behavior of the volcano. And just for a quick summary for anyone who's not that familiar with Cooke's classical model, basically we seek to calibrate or measure the statistical accuracy and informativeness of individual experts on a set of seed questions. We do that and get some measures of how statistically accurate and informative they are, and we can then combine them and produce a synthesized judgment from the group. And my motivation for doing this was that I've been involved in eruption crises before over the last 50 years, and the chief scientist usually becomes the scapegoat or the person hung out to dry when things go bad. And it seemed to me this was a way to depersonalize scientific advice and allow the scientists to concentrate on the science and less on the implications in front of the media. Just a slightly complicated slide. After we'd been doing this a little while in Montserrat, on the right-hand side, we get this fairly typical profile, statistical accuracy on the bottom, multiplied by informativeness to get a score. And these are a typical profile of experts, in this case, 18 volcanologists. And there are interesting things about this. By and large, senior, experienced volcanologists are the ones whose judgment is worth listening to. But there are exceptions, like number 2 down here, who was a well-known international volcanologist, and number 3, poor judges of uncertainty. And if they said, let's go and climb the volcano this afternoon, the wise move was to think twice and go and find something else to do. And we checked this against a bunch of probabilistic hazard assessors in earth sciences. They weren't volcanologists, but they were, you know, seismologists and geologists and so on. And what this demonstrated was that the opinions of the better volcanologists are stronger and more worthwhile than neutral people and than a lot of the others. And this is a fairly typical profile that we've seen in all sorts of scientific and engineering disciplines. So this was the basis for providing advice to the politicians, the military, blah, 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 during an ongoing crisis that, you know, went up and down and was evolving as it progressed. One of the things we did was to produce forecasts for what might happen in the short term and the near term, because that would dictate what mitigation measures were taken. For example, if the first thing that came out, the first thing that came out was a dome that was relatively slow, it gave the civil authorities time to react. They could evacuate the elderly and kids and leave the able-bodied in place. If it's going to be an explosion in the next 24 hours, then, you know, everyone had to be got out. And what happened over these three separate elicitation forecasts was that the red line pretty much followed the highest or higher probability branching in all cases, except the very first, when the unrest, it's not clear whether it was going to be magmatic or non-magmatic. 0.58, 0.42 is basically 50-50, saying, well, we just don't know, it's a toss-up. But after that, the forecast tended to be the things that the group as a whole thought were most likely to happen next. We are often told we don't convey these communicate these things very well. So here's a little semi-serious slide showing if you'd invested £1 on our forecasts in 1995, over the following 13 years or so, your investment would have been more than £30. And at the same time, if you had put your pound on the stock market and had a FTSE tracking thing, it would have been worth a few pennies more than it was at the start. So the message here was that you are better off, if you're a politician, listening to scientific advice than tossing a coin or listening to charlatans. And there are quite a few of those around at the present. We also developed societal risk estimates, and these again are slightly busy things. Anyone who's familiar with FN curves will know about them. It's basically a log-log plot, and typically for industrial facilities where they're most commonly used, you get a single straight line diagonal across the plot. Below that is tolerable risk, above that is a LARP or intolerable. The thing about volcanoes and why these curves are not straight lines is that the volcanoes have more ways of one than killing you. The threats from pyroclastic flows, ashfall, earthquakes, tsunamis, any of which can kill you. And with this, we tracked over sort of every 6 months or so how we perceived the risk to the population of Montserrat going up or down in time. We could convert that, for example, if we take one case, December 1999, there's the baseline, base rate societal risk. We could tell the local government, well, if you move people further north, you can reduce societal risk. If you take them even further north, it can come down further. We did not make the decision about moving people or evacuations. That was a political decision. It was just, we explained the choices and the implications that arose. And all this, again, informed by expert elicitations, because we're dealing with, all volcanoes are different and they never erupt the same way twice. So it's an evolving, non-linear stochastic process. One of the other issues when you get into risk evaluation, people say, oh, well, you know, how does this risk compare with rock climbing or, you know, bungee jumping or whatever, and smoking cigarettes? These are usually not very good comparators. So what we did in Montserrat, we said, well, in the region, people live long-term with hurricane and earthquake hazards, and therefore here's the volcanic risk. It's way above either of those two, but if you move the exclusion zone, Mr. Governor, Mr. Prime Minister, you can reduce your societal risk level to be commensurate with what seems to be acceptable to the population living in the Eastern Caribbean. But again, as I stress, the decision to act on this is the politicians, not the scientists on that. We also looked at individual risk exposure estimates, and so this is the annualized individual risk of death by volcanic action in different parts of the small island. The volcano occupies a third of the whole island, so it's kind of hard to get away from it on that. And you can see different probability levels. And because of this issue about how to communicate risk, initially we adopted the British Chief Medical Officer's risk range vernacular scale: moderate, moderate, low, low, very low, and so on. This again turned out to be a mistake, because this scale was devised to express to, I think it was women who were going to have a certain operation, the risk of the intervention. Now, obviously, you know, what is regarded as a moderate risk in an operating theatre for one woman in Britain is not probably the same as other people would perceive the risk to them from a natural hazard in this case. So eventually we abandoned this again. And this is the reason I keep stressing some of this, is we learned quite a lot over 20 years in Montserrat about what not to say to politicians and the public. And it's very regrettable for the last 12 to 13 weeks to see British scientific advisors and politicians making the same mistakes that we learned to avoid on that. The other one, a particular bête noire of my own, is traffic light alert systems and so on. And of course, we now know that the British government is tying everything on their 5 tests. We've tried this at volcanoes over the years, and in fact I also worked on this with British Airways several years ago on reducing flight operation risk. These simplistic alert level schemes always fall apart when you're dealing with natural phenomena like volcanoes, earthquakes, or even pandemics. We compromised in Montserrat by eliciting from our group of scientists what I call their relative anxiety about the alert level. For that, you could read confidence in the present alert level. So we had, again, a depersonalized, semi-objective way of synthesizing from the group, did they feel the alert level was appropriate? Because if you're sitting in the middle of amber, everybody's agreed it's a consensus and everything's straightforward, wonderful. What happens when you start to creep up and think, oh, we've got to go to red, or we've got to evacuate the whole island? Then things do get very, very tricky. So we tried to make that less subjective and if possible. But again, I stressed the decisions to change the threshold were the ones for politicians, not for us as scientists. We could just tell them, we really think, you know, you ought to be up 1 or down 1, but they were the ones who had to take responsibility for doing it. Moving on, as I said, I've done a lot of these elicitations in connection with Montserrat. I've also done quite a lot in connection with other problems in public health and other areas. And back in 2004, when SARS was threatening to come, you remember there was an outbreak in Southeast Asia and then in Canada. And we did an expert elicitation at Addenbrooke's in Cambridge about the efficacy of different protection, PPE as it's now called, for healthcare workers, and what's the appropriate level on that. This slide, I'm afraid, is a little bit busy, but basically our finding at that time was that the conventional statistical methods and epidemiological surveys were of limited use in that. The protection of disposable respirators was thought to be adequate, but note that the experts, the clinicians and nurses that we elicited, all felt that they were less effective than test results and manufacturers' claims. And there were severe doubts over the benefit of ordinary surgical masks. We did this and converted it to something of a risk assessment for nurses who might be confronting SARS, and came up with an estimate of about 8 per 1,000 for a healthcare worker wearing a face-fitted N95 mask, which is about 8 times higher than the tolerable occupational risk for a nurse in the UK. So it was clear from this that they were going to have to do something much more significant than just give surgical masks or even N95 masks out. So there's an awful lot of deja vu in my world at the moment, seeing these things come back and being rediscussed not very well. So where have we got to with the Royal Society ramp thing? We've been trying to insinuate ourselves into that and trying to transfer our volcanic risk assessment to the present crisis. And we've been building Bayesian belief network, uncertainty models using expert elicitations. And I'm very much of the view that any such model for live management of risks and hazards has to be as simple as possible. There's a great temptation to have all singing, all dancing. I've got colleagues in Italy who got computer programs for volcanoes that need a supercomputer. And, you know, if you want a prediction for tomorrow, well, you have to wait a week because it takes them a week to run their incredible, computational fluid dynamics models. And I sense there's a bit of this going on with epidemiological models that are being used by the SAGE. Not too clear just how manageable and tractable they are in an emergency and urgent work. So this is just a very simple thing that Steve Sparks and I have been doing in connection with the return of primary school kids. And we were just looking at the relative impact of the year 1 children, nursery reception in year 1, year 6, and the children from protected things, and adults, teachers, teaching assistants, cooks, and so on. And the big unknown here, the big parameter that really, oh dear, I don't know where to start, R0. It's quite clear, I think, that it's not a risk metric, and that it actually hides quite a lot of dodginess on that. Anyway, we thought we'd put one together to say what would happen if a child turned up at school, and this is just using the Roger Cooke's Uninet Bayesian belief network software package, which is extremely easy to use, graphical. So we've got uncertainty distributions down the left here. R0 is the one that we had no real data for, so we elicited some judgments about potential values and ranges, and we just wanted to estimate the probability of an asymptomatic incubating person coming into school on day 1, or somebody who's asymptomatic and already infected coming in, because these have different time constants in relation to infectivity and transfer. And this is conditionalized for the model is set up for a 5-day week, 1, 2, 3, 4, or 5, and in this case we conditionalize the general model on day 1, and we come up with a probability in an average school of about 13% that there would be at least one infected person present among the kids or the staff who had the potential to spread it. The point here is that we want to get away from just simple averages, so we use uncertainty distributions, and the 95th percentile of this black distribution, 0.3, which is a pretty high, 30% probability, is pretty high if you regard this as a undesirable threat or hazard. If we conditionalize now on the full 5 days, the fact that, you know, somebody has turned up on day 1 carrying the infection and isn't detected, then the probability it will spread in the school within that 5 days is about 39%, 40%, and we're up to 95th percentile of about 65%. So you aren't going to get away with much putting kids in school if you, just in terms of infections. I'm not talking about, you know, whether the kids actually suffer from this, whether, you know, it's bad for them, but they then are in a position to spread it to other kids and then back into the wider community. In support of this, we've been doing an expert elicitation with primary school head teachers through the Royal Society. We've had a wonderful response. More than 36 of the heads on the Royal Society's education group have actually taken part in that, and this is showing the sort of problem we get. We ask them to forecast what percentage of pupils would be coming back on the 1st of June, you know, from their judgment. And you can see we're into a very wide uncertainty range with multimodality, and there's clearly a lot of heterogeneity in here. Depends on school size, location, whether it's co-ed, whether it's in an urban setting or rural setting, and so on. And we're trying to break this up now and find how we can use that. And I just move on, finally, a couple of more slides. We also have been using the same Uninet package to estimate the number of primary schools that may have coronavirus infections following a partial restart on that. And again, we find this particular package easy. I've used it over the years for volcanoes and, you know how to drive it, but it is easy to quickly set up, you know, a stochastic uncertainty problem on that. And in this case, we include children, teachers, teaching assistants, and ancillary staff, and their probabilities of attendance on day 1. The details of the actual Bayesian belief net model don't need to concern us too much. Basically, we've got kids in blue, teachers in light purple, teaching assistants and ancillaries, and combining these, you know, in a sort of Monte Carlo simulation way to work out the bottom line. We were the number of schools, primary schools in Britain that are likely to be affected. There are 16,769 primary schools in England. Sorry, this is all England, not England, not even Wales, not Britain. And this is a sort of typical finding that we can get there with the assumptions and uncertainty distributions. The mean number of infected children as of day 1, 2,210, plus or minus 1820, 357 infected teachers, and 2,550, give or take quite a lot, of schools with at least one infected person. As I say, there are 16,000 schools. So we're talking about a significant percentage of primary schools in England will have infected children in them on day 1 on that. And again, a point here that many of you will easily appreciate, it's the tails of these distributions that are important. If you just stick to the average like R0, you lose sight of what might be actually driving disasters, which are the extreme values. And again, one of the strengths of this particular package is we can instantiate or conditionalize particular values. And here I just done this and said, well, maybe parents will, only 50% of the kids will come back because the parents will restrict it. Maybe only 51% of teachers will attend because they're shielding or they've got parents and blah, blah, blah. And you can update that. So now If you have these conditions, we now expect 276 teachers to be infected, compared with 357 before. Right, I'm winding up, Philip, and we can also do sample-based conditioning on that. So here are two of the nodes from that, their full range of values and the distributions there. We can then say, well, I'm only interested in this narrow range from each of those. And then at the bottom, we can see the impact that has on the target nodes. In the case of number of infected teachers, these conditionalizing intervals will take 357 down to 284, and the percentage of schools with an infection down from 15 plus or minus 8% to 10 plus or minus 5%. So, summing up, as far as I can see, the people advising SAGE and so on are not doing quantitative risk analysis in the way that I would understand it, and most other risk analysts would understand it in terms of societal, occupational, or individual exposures. And I keep asking, why do I not see the HSE in this, given, you know, schools, courts, everything else and that? We can use structured expert judgment to counteract flawed reasoning, and I've done it in the past for SARS, variant CJD, the notorious XMRV infection finding, and so on. So it's well suited to a new emergent zoonotic virus like SARS-CoV-2. The scope is wide. And finally, famous last words of a volcanologist: I'm good at predicting eruptions, and I think we can pretty much read, for volcanologists, read epidemiologists these days. So there's my manifesto, and you know, that's a quick run through it, Phil.
That's great. Thank you very, very much indeed, Willy. That was fascinating. And I think I will be contacting you privately for a bit more background on that, because I'd like to know more. There's very little time for questions. There's only one, and that was, oh, sorry, no, there's two. I said one, but I think I'll do the one that I didn't put in. Okay, the classical method provides estimates of parameters. Have you made progress on structural uncertainty? Alternative models of cause and effect.
Have we made progress on what? Sorry, I didn't catch.
Structural uncertainty.
That's no. I've you know, I know that there are other people are working on these things, and again, I use this Rogers method as a practical tool. It's got limitations. It could be improved, perhaps. But it seems to work, and the key thing is that over the years we found experts, once they understand the basis for it, are happy to use it for that purpose, to synthesize a collective judgment that gives a sort of snapshot of uncertainties as they're viewed at this time. It's not intended to be, you know, definitive research finding. Somebody's got to make a decision by 4 o'clock this afternoon. Do we move the population or not? And this has been found to be one approach that, the background to this, Phil, is that when we started doing these things on the first day in Montserrat, we met for an hour before the governor and the chief minister came, couldn't arrive at a consensus. The next day we met 2 hours before they came and couldn't arrive at a consensus. So eventually we adopted this as a way of stopping colleagues wasting a lot of time arguing in a sort of committee mode.
That's great. Thank you very much indeed, Willy. I remind everybody that we will have a more extended question and answer session at the end of today's talks at about, what time are we going to do that? I think it's about 4 o'clock. But you can, and anybody can submit questions at any time on Slido. Please look at the chat for details of how to submit questions. I hope you will.